Hello, Chem 1B. This is Chapter 19, Lecture Video 7, and we're going to kind of bring everything home here for all the chapters we've covered in this class up to this point. When we first started covering material in Chem 1B, we started with kinetics, right? And we learned that at equilibrium for any reaction, the rate of the forward reaction is equal to the rate of the reverse reaction, which means our rate laws are equal to each other for these two. And this directly ties into equilibrium, right? Equilibrium is equal to products over reactants. Yes, that's the one we commonly remember, but it's also equal to the forward rate constant over the reverse rate constant. So there's a direct link between kinetics and equilibrium. Then in chapter 18, we started talking about how equilibrium relates to thermodynamics. We know that there is a relationship between the equilibrium constant and delta G. And then in this chapter, we talked about how delta G relates to E naught cell and how equilibrium constants relate to E naught cell. So as you can see, these all kind of interlink together. So all the chapters we've covered in this class up to this point are all very related to each other. And if I'd wanted to, I could give you the rate constant for the forward and reverse reaction and ask you to calculate delta G or E naught cell. Probably won't do that, but it is what we do on our thermodynamics worksheet that you guys will be doing in the class. So you kind of go through all 4 steps. All right. So the rest of this chapter is going to be on what we call electrolysis. And electrolysis is different from a voltaic cell. So in a voltaic cell, generally we have electrons spontaneously flowing from the anode to the cathode. This really means that we have a spontaneous redox reaction. It's going to produce electricity in a voltaic cell. These are like batteries. In electrolytic cells, we have an external power source with an electric current driving a non-spontaneous reaction. In other words, in an electrolytic cell, we're forcing a non-spontaneous reaction that normally wouldn't happen to happen. This is useful in many different ways. For one, if you've ever thought about, hey, cool, my battery died. I'm going to go plug it into the wall outlet. And then we charge it. And then our battery works again. Well, how's that happening? Well, when your battery is powering your device, it's a voltaic cell. When you plug it into the wall and start charging it, it becomes an electrolytic cell. We're forcing the reverse reaction of the battery to build up our reactants again so that our battery can function and power our devices. Another aspect that is very useful with electrolytic cells is that this redox reaction, hydrogen and oxygen reacting, going to water, is a spontaneous process. But sometimes we want the opposite to occur. We want to break apart water and form hydrogen gas and oxygen gas. This doesn't happen without outside intervention. And what we can do is we can drive this reaction to occur using an electrolytic cell, forming hydrogen and oxygen gas, which is super useful. It's actually how a hydrogen fuel cell works, especially when it's coupled to a solar panel. So a lot of times solar panels will generate more electricity than what's being used throughout the day. And what you can do with that extra energy is run it in an electrolytic cell with water, cause the water to break apart into these two during the day, and you can separate them and store them throughout the day. Then at night, when there is no sun, you have these two react like this in the spontaneous version, creating energy that can power your house. And so there's a lot of engineering that goes into these two processes. Effectively, what an electrolytic cell is we're using electricity from a secondary source, like a battery or something else, to drive a non-spontaneous reaction into occurring. And this is basically what I kind of talked about with the hydrogen fuel cell. We'll talk more about them later. What is electrolysis? Continuing on that topic, right? In a voltaic cell, to review, The anode is the source of electrons. The electrons are moving from the anode to the cathode. It has a negative charge. At the same time, the cathode is drawing electrons towards it. It has a positive charge. In an electrolytic cell, there's some very slight differences in these definitions. Electrons are drawn away from the anode. Still, the anode is our source of electrons, but it's being drawn away because of an external power source, not because of the cathode drawing the electrons towards it, but because we're forcing the electrons to move away from the anode by attaching an external power source. Again, electrons are being forced to go to the cathode. It must be connected to the negative terminal on an external power source. The anode must be connected to the positive terminal. This causes the electrons still to move from the anode to the cathode in an electrolytic cell, but it's not a spontaneous process. So, kind of looking at an example here. This is our galvanic or voltaic cell. We have the zinc and zinc 2 plus being oxidized here. We have the copper 2 plus being reduced, and it's creating a positive voltage, about 1.10 volts. In our electrolytic cell, we have a slightly different scenario. Notice we have an external power source, a battery. It needs to have at least the same voltage as the galvanic version of our cell. In this case, if you look at this, the anode is still where oxidation occurs, the cathode is still where reduction occurs. However, what is being reduced has changed, right? This was the oxidation over here. This was the reduction. Over here now we have a reduction of zinc. And here we have the oxidation of copper. So still, this is the anode, it's the oxidation. This is the anode, it's the oxidation. Cathode's still where reduction occurs, but now the opposite reaction that didn't want to occur originally is now occurring, and we're forcing a non-spontaneous process. The electrolytic cell has a negative 1.1 volt cell potential, which means that we need to have a battery or an external power source that has more than 1.1 volts. This will cause the reverse reaction to occur. So we can predict products of electrolysis. Now for pure molten salt solutions, which basically means we have like NaCl liquid. So we heated this guy up to a really high temperature, we melted it. The cation is going to be reduced and the anion is going to be oxidized in a pure molten salt solution for electrolysis. In other words, in NaCl, we have Na being reduced to Na solid, and we have Cl minus being oxidized into Cl gas. In a molten salt mixture, this gets a little bit trickier. If we have these two both present, the cation, which will be reduced, is the one with a more positive electrode potential. So these are basically just E0 reductions. The one that's more positive is going to be the one that actually gets reduced. So in this case, it's going to be the Na because it's slightly more positive than the potassium. Okay. In a molten salt mixture, let's say we have these two again. Let's talk about the anion that's going to be oxidized. It's the one with the more negative electrode potential in this case. So we already said it's going to be sodium's going to be reduced based on their electrode potentials. If we look at Cl versus Br, it's going to be Br that gets oxidized because it has the more negative potential. Again, these are effectively just reduction potentials that we could look up. So in aqueous solutions, slightly different. We're not going to really cover those as much Aqueous solutions, they're much more complex due to the fact that you could be electrolyzing or you could be doing the electrolysis of water, which adds a lot of complexity to the system. We're just not going to get into it. And to be honest, this molten salt mixture thing, I won't be testing on it. It might be on your homework though. What I will be testing is electroplating, because I think it's kind of neat. Using electrolysis, we can do something called plating metals. For instance, if you ever bought silverware that was silver plated versus silver, silver plated means that you've put a very thin layer of silver over another metal, and gold plated means the same thing. It's not pure gold. There's some other metal, and you have a small thin surface of gold around that other metal. This is what we do for pennies. Pennies these days are made by zinc discs, and you plate out copper in a thin layer around the zinc disc. It's kind of neat. So if we wanted to plate, for instance, silver on a surface, we need to take into a couple things into account. So here's our electrolytic cell. We have our battery. It's causing the silver aqueous to be reduced into the solid state. And we're going to hold our spoon in there if we wanted to plate a spoon silver. There's a couple variables that we need to know. We need to know the current of the battery. We need to know how many moles of electrons I need to actually get silver, in this case, to go from silver plus to silver solid. In this case, it'd be 1 electron because of the +1 charge. But other metals have different charges, so it might be a different number here. And time. The longer you run this cell for, the more silver is going to be plated out. Finally, we also need Faraday's constant. That's just a value we're going to need to do the conversions. So for plating silver, as we've just talked about, you need Ag plus to go to Ag solid, meaning I need 1 electron. That's this guy. So let's do an example question. If we have a battery with a current of 4.67 amps, and we run this electrolytic cell for 34 minutes, we want to know how many grams of silver could be plated. Now this is just one example problem for electroplating. We could also be asked how long it would take to plate a certain amount of grams, or what current would be required if we wanted to plate this many grams in this amount of time. Any of those three are fair game. But in this problem, we're asked for grams of silver. Now, using the current of the battery, the time we ran the cell for, and Faraday's constant, we're going to find that we can get moles of electrons. And with moles of electrons, if I know the reduction half reaction for silver, I can get a mole ratio for electrons to silver solid. Once I have that mole ratio, I can go moles of electrons to moles of Ag. And once I have moles of Ag, I can get grams of Ag. Now, if we're doing this, one thing to think about is that 1 amp, like I'm saying here, is equal to 1 coulomb per second, which means that our current is 4.67 coulombs per second. And if I take my 34 minutes that I ran this cell for and go, hey, there are 60 seconds in 1 minute, and 4.67 seconds is how many 4.67 coulombs in 1 second is my current. I can get coulombs, all right? And so if I calculate that value out just as a placeholder here, we get 34 times 60 times 4.67, which gives me 9,526.8 coulombs. Now, if I take that and Faraday's constant, this is units in joules, volts, moles, electrons. We can also write Faraday's constant in a different set of units, which is coulombs per mole of electrons. So if we think about that, I have 9,526.8 coulombs. And if I go, hey, divide that by Faraday's constant, I can get moles of electrons. Coulombs cancel. Then I can use a mole ratio here between electrons from my redox reaction, my reduction half reaction. I know that 1 mole of electrons in this reaction gives me 1 mole of Ag solid. And I know the molar mass of silver is 107.2 grams per 1 mole of Ag. If we do all of this out, right, moles of electrons cancel, moles of silver solid cancel, we're left with grams of silver, which will give us the mass that we plated out on this spoon. Which gives me about 10.5 grams of silver, or to 2 sig figs, 11 grams of silver are plated. So this is an electroplating problem. The rest of this chapter is going to be on batteries, and I'm not going to test you on batteries, but there is some problems on your sapling homework with batteries involved. So for standard alkaline batteries, they follow a redox reaction. These are all voltaic cells. So at our anode, we have oxidation still. We are oxidizing zinc to zinc 2+ in a basic environment, which means we're going to form zinc 2 hydroxide solid. It's an insoluble salt. At the cathode, we have reduction. So we have manganese 4 oxide being reduced to manganese 2, whatever this is. It's a complex name. We're not going to deal with it at this point. But both are in a basic environment. With the concentrations at their initial values, most of our general alkaline batteries will generate about 1.5 volts. So this is a regular D battery. You can kind of see that we have a paste here in this part of MnO2 and NH4Cl. NH4Cl's just kind of helping the process a little bit. We have a metal casing. That's our anode. And the anode's going to be made of zinc because we have zinc solid here going to zinc hydroxide. Now over time, this paste starts to become the products of these two half reactions as it generates more electricity. A standard 9-volt battery, like the one with the 2 terminals on top, is really the same thing. It's still these same half reactions, but instead of 1 cell inside, we have 6 of them. And 6 times 1.5 volts each, if we put them in series, gives us a total voltage of 9 volts. Again, not a big deal, not something I would ask you on a test. Okay, another type of battery is a lead-acid battery. These are your typical car batteries. Lead-acid batteries involve, guess what, lead and acid. Crazy, I know. But the anode is the oxidation of lead solid into lead 2+ in acidic environment. Usually sulfuric acid is involved. The cathode is the reduction of lead 4 oxide to lead 2+ again, in this case sulfate. These 2 cells give you about 2 volts each. Now, car batteries have a lot more than 2 volts of potential. And the reason why is because we have a bunch of these cells inside this battery. Unlike a dry battery, we can recharge charge a lead acid battery by using an alternator, right? The alternator allows for putting in an electrolytic current type scenario back in, recycling the battery, basically making the battery's reaction go in reverse to repopulate with, refill our reactant concentrations so that it'll work again. Okay, so hydrogen fuel cells are pretty neat. They work based on hydrogen and oxygen coming into a tank, and then an electric current being created from that as the two react to form water. So there's very little pollutants involved in hydrogen fuel cells. There's still materials within the fuel cell that are toxic, but the main product of this system is water. So very, very kind of clean energy here. And they're very related to a lot of solar technology, because solar panels don't work at night because the sun's not out. And so what you can do is you can have the solar panel run this cell in reverse, right? Have it do electrolysis during the day, forming H2 gas and oxygen gas, and then at night we have the reverse curve. The oxygen gas we form during the day comes into our fuel cell and powers our home. Each one of these cells produces a pretty significant amount of voltage, at least at their initial concentrations of everything, and it's about 3 volts. And usually we wouldn't just have one single cell, we'd have multiple cells if we were using this in tandem with, solar. It's a pretty neat system. There's a lot of research going into fuel cells, especially in ties to solar technology. So it's kind of a big deal these days. All right, so as always, if you have any questions, feel free to ask me via email or in my discussion meetings.